Hey guys, welcome to Unit 4 Physics. Today we're looking at our Introduction to Special Relativity. In particular, our learning goal today is to describe an example of natural phenomena that cannot be explained by Newtonian physics, such as the presence of muons in the atmosphere. So we're really looking at muons today. We're going to learn what those guys are, and we're going to refer to them quite a bit throughout our special relativity unit over the next couple of weeks. So let's do a quick recap of Newtonian physics. What we know about Newtonian physics is basically everything we currently understand about motion from our physics course so far. So we've got our, our F equals ma, Newton's laws. We've got our vectors. We've got all of our Suvat equations. So they're our kinematic equations or equations of motion. Okay. We've been looking at x, y coordinates. Some of you in specialists have been looking at the x, y, z plane. And in space, when it comes to Newtonian physics, it's really easy to find the distance between any 2 points with Pythagoras. And you're able to work this out quite simply. The other thing in Newtonian physics, other than our three-dimensional space, is our linear understanding of time. Okay, so not only does time go forwards, but 1 second here in Brisbane is the same as 1 second over in Perth, is the same as 1 second on the top of Mount Everest. It's the same as 1 second in deep space and so on. So this is our current understanding of Newtonian physics, okay, just before we get started. So the next thing we're going to, just checking if it's recording because it hasn't recorded the other times I've done this. The first thing we're going to talk about now that we've recapped our Newtonian physics, is muons. So what is a muon? Here's the Earth, okay, and then about 10 to 15 kilometers away is the outer atmosphere, okay? That's 10 to 15 kilometers away. Now, in the upper atmosphere of the Earth, we have a lot of atomic nuclei, okay? One of the common atomic nuclei we have up there is oxygen. The other thing you may be aware of is this big shiny thing called the sun and all this stuff outside here called space. Okay, so every now and then we get this really high energy cosmic radiation, and when I say every now and then, I mean constantly hitting these nuclei, all right, at the very outer edge of the Earth's atmosphere. Now, when that happens, something really cool comes out, an elementary particle called a muon. We denote that with the Greek letter mu. Now, a muon is an elementary particle, and it's approximately 207 times heavier than an electron. All right, so you can think of it as a big fat electron, basically. Now, the mean lifetime of a muon is about 2.2 microseconds. So what happens is when that muon is formed, it travels towards Earth at a really ridiculously high speed at about 99.97% of the speed of light. Okay, but it only lives for a mean lifetime, or it has a mean lifetime, of 2.2 microseconds before it decays into other particles. So if I do a quick calculation based on Newtonian physics, we know that the displacement of an object is the product of its velocity and time. All right, so if I think of 99.97% of the speed of light, that's 0.9997 multiplied by 3 by 10 to the 8, multiplied by the mean lifetime in seconds, so 2.2 by 10 to the minus 6 seconds, means that after about or approximately 660 meters, most muons should have decayed because that is their mean lifetime. So if I'm thinking about this 10 to 15 kilometers away where they're formed, pretty much nothing should be detected down here on the Earth's surface. Here's the problem though. They are. Okay? So this is where Newtonian physics doesn't work anymore. All right, so we've got muons. There are elementary particles that are created in the Earth's surface, and they should not be detected at the Earth's surface, but they are. Okay? So what do we do about this? This is where we need a new theory, and this is what we're going to be working on. Okay? Special relativity. To continue with special relativity, so we had this idea of Newtonian physics, and it's sort of starting to not break down, but it's not really working for us at the moment. Our experiments and our theory aren't matching up. We also have Galileo, another famous scientist who I'm sure you've all heard of. He definitely had a contribution to this field as well. And he had his own principle of relativity, and it basically says this: you cannot tell if you are moving without looking outside your frame of reference. If you think about yourself on an aeroplane, okay, and say that aeroplane has no turbulence. This is my aeroplane. Yeah, aeroplane. Say that aeroplane has no turbulence, okay, it's smooth sailing. You can't actually tell that you're moving unless you look outside and see the clouds going by. The same is true for a car. The same is true for everything. All right, you might have had a situation in traffic where traffic is moving really slowly, but you're actually stationary, and a car is moving around you, but you're actually not sure if you're moving or the car is moving. And that's a really cool thing to think about, because sometimes you don't know, right? You cannot tell whether you're moving unless you look outside of your frame of reference. That's how we know we are moving, okay? The other cool thing that Galileo came up with was this really nice thought experiment. So his thought experiment went something like this. You have a boat moving at constant velocity v, all right? And a person on the boat drops a ball, all right? According to the person on the boat, the ball is going to fall directly downwards, completely vertically. All right, they're going to drop the ball. It's going to land directly below them on the ship deck, okay? But now let's consider there's the person on the boat traveling at constant velocity v. They're standing up here on the mast because they're real cool with their captain's hat on, because that's pretty important. All right. But now we have over here on an island an observer, and this observer is stationary. As this observer is looking at the person dropping the ball, okay, something really interesting happens. Okay, in the next point in time, we can agree that the ball is going to end up here on the ship deck, but rather than traveling straight down like it does according to this person's point of view, the person on the island is going to see it travel in a parabolic path, which is a really cool thing to think about, okay? And this guy here is not going to really understand that because they see it happening over here. So this is one of Galileo's thought experiments, all right? And this goes on top of not being able to know whether you're moving without looking outside of your frame of reference. But rather, this person on the boat and this person on the island see different things because they're not in the same frame of reference. We're going to talk more about frame of references in our next lesson. But let's talk now about relative velocity, okay? And I want us to think about a situation where there are 3 cars on a highway. So we have this car, car A, traveling north at 80 kilometers per hour, according to a tree on the side of the road. Now the tree is not moving. In the lane beside us, we have car B. Car B is also moving north, but a little bit faster. 90 kilometers per hour, according to our leafy friend. On the other side of the road now, we have car C. And car C is traveling south at 80 kilometers per hour. Again, according to our tree. All right. Now, here's where it gets really cool. I want you to imagine yourself in this situation. And let's say that you are the person in car A. Now, when car B overtakes you, you don't perceive them as traveling at 90 kilometers per hour, but rather you perceive them as traveling 10 kilometers per hour according to your reference frame. Similarly, if you were to come and see car C traveling in the opposite direction to you, you don't see them traveling at 80 kilometers per hour, but rather you will perceive them relative to you traveling at 160 kilometers per hour. And these values here in red, guys, are what we call the relative velocities. Okay, so how do we calculate relative velocities? There is a formula. Here it is, but this formula does depend on having a common observer in both situations. All right, so the velocity of A relative to B is equal to the velocity of A relative to an observer minus the velocity of B relative to an observer. So let's consider the example we had on the previous slide. Car A and car B, this one's traveling at 80 kilometers per hour. This one's traveling at 90 kilometers per hour. Okay, according to the tree, who's our observer O. If I was to work this out mathematically, if I'm trying to calculate A relative to B, so that means I'm talking about B's reference frame. A relative to the observer is 80 kilometers per hour, and B relative to the observer is 90 kilometers per hour, which means A relative to B is negative 10 kilometers per hour. And what you'll actually notice, guys, about that value is that's actually equal to the negative value of B relative to A. So on the previous slide, I said that we would see this guy traveling at 10 kilometers per hour because they're traveling faster than us, but he sees us as traveling at negative 10 kilometers per hour. So this statement down here at the bottom is also always true. Okay. Now, let's have a go at a couple of questions. These questions here are from your textbook in chapter 10.1. Please pause this now and have a go. All right, let's do question 1A. Question 1A is to do with your car. I'm going to say A is my car and B is the Hoon's car. So just like in every time we have to define a variable, it's nice to draw a diagram and denote this or simply state your variables. So I'm looking for the velocity of B relative to A, the Hoon's car relative to my car. So that's going to be the velocity of B relative to a common observer O minus the velocity of A relative to a common observer O. And what you notice here is that B relative to A, we always put B relative to the observer first and A relative to the observer next. So we're always working from left to right. If I pop those values in, I get 120 kilometers per hour minus 100, which gives me an answer of 20 kilometers per hour. All right, so the Hoon is moving at 20 kilometers per hour relative to me. The next thing I want to work out is the velocity that the Hoon sees me traveling at. So VA relative to B. All right. And guys, I'm just going to make the statement here. That's negative, the negative of V, B relative to A. Okay, so that's going to give us negative 20 kilometers per hour. So I see the Hoon traveling at positive 20 kilometers per hour because they are traveling faster than me. The Hoon sees us as traveling at negative 20 kilometers per hour. That's the same as if someone is sitting down by themselves and a runner is running past them, okay? That person is going to be off in the distance. All right, it's the same thing. Let's now have a look at question 2. Question 2, we've got Mel walking on a bus. All right, so for question 2A, the velocity of Mel relative to the road, well, she's just sitting on the seat. The bus is traveling at 5 meters per second, so Mel is also traveling at 5 meters per second relative to the road. All right, that's not meant to be a trick question. Part B is a little more tricky. We're looking for the velocity of Mel relative to the road. Oops, I meant to write Mel there. Velocity of Mel relative to the road. But we need to consider the common observer. And the common observer here is going to be the bus. So that's the velocity of Mel relative to the bus minus the velocity of of the road relative to the bus. Okay, and just like before, you notice here we've got M and R, and M and R, and then our common observers. So, whoopsies, let's just delete that one. All right, so the velocity of Mel relative to the bus. Well, Mel is walking at -1 meters per second according to the bus. She's traveling in the opposite direction to the bus, right? But the velocity of the road relative to the bus, it's the same as the bus relative to the road, but in the opposite direction. So that's -5 meters per second. So the bus perceives the road as traveling backwards or behind it. If I pop that together, I get my answer of 4 meters per second. That Mel relative to the road is 4 meters per second. So in other words, if we had a tree, all right, looking at Mel walking to the back of the bus, they would see her walking at 4 meters per second. And this goes back to our sailor example, when you have the person on the island looking at the ball. All right. With that, guys, I now want you to go to chapter 10.1 in your textbook and have a go at the textbook review. We're going to move on to frames of reference next lesson.